Well, good morning, ladies and gentlemen. This is 10 Years Hence. I'm Professor Jim O'Rourke from the Department of Management and Organization, and welcome to the fifth in our series, Life Beyond Earth. Robert Jedicke is a professor of astronomy and an astrophysicist at the University of Hawaii, explaining, of course, the aloha shirt he's wearing today. I was unable to talk him out of that. Professor Jedicke has had professional careers in particle physics, astronomy, and software engineering. He received his PhD in experimental particle physics from the University of Toronto, Ontario, Canada. After a brief tryout with the BC Lions, professional Canadian football team in Vancouver, he held postdoctoral positions at the Fermi National Accelerator Laboratory in Batavia, Illinois, and at the University of Arizona's Lunar and Planetary Laboratory, where he worked on the Spacewatch Near-Earth Asteroid Survey. He spent more than 5 years at Vico Corporation in Tucson, Arizona, developing image analysis software for interferometers before accepting a faculty position at the University of Hawaii's Institute for Astronomy. He was the development manager of their moving object processing system for the Pan-STARRS telescope on Maui that is now the world's leading discovery system for asteroids and comets. His current research includes working with Transastronautica Corporation to develop techniques for mining asteroids to provide water as fuel for spacecraft missions. Ladies and gentlemen, please help me welcome to the Notre Dame campus and the College of Business, Professor Rob Jedicke.
Thank you very much for that kind introduction and for the invitation to come to speak here at Notre Dame. It's my first time at Notre Dame and also my first time seeing snow in about 5 years, I think. I forgot that it snows places, and I was glad to have gotten the reminder that I needed to bring a jacket. The shirt that I'm wearing is obviously a Hawaiian shirt, worn in your honor. I don't own a tie, jacket in Hawaii. Everything's very casual. But I had a sort of a discussion with my wife about what I should wear, and she said, no, you have to wear a Hawaiian shirt. And I said, no, I want to wear my Asteroid Day Crew shirt. Because I fear I'm talking about asteroid mining, so I should want to, I want to support my asteroid mining people. So I am going to wear my Asteroid Day Crew shirt. So, but it makes me look a little more like Steve Jobs here. So. So here's my Asteroid Day Crew shirt. I think it's a little bit more appropriate for this talk. So I think you must have a really great, I took a look at all the lectures that you have here, and the series looks really fabulous. And because it's a business school, most of your programs are talking about business. Of course, most of the time I talk to people about astronomy. And so it's a little unusual that when I give a talk about astronomy, it's actually not about astronomy for me. It's actually all about the money, because I'm in the asteroid mining industry to make money out of it. And full disclosure, I work with a company called Transastra. Transastra is an asteroid mining company, although I think that really doesn't do it justice. It does a lot more, and I will tell you about that in the next few slides. Transastra is what I would call a vertically integrated asteroid mining technology development company. The whole goal is to create or participate in a space industry, and they have a real vision for it. It's not just asteroid mining. I do asteroid mining because that's my specialty. I've been working in asteroids and comets for 30 years. But they have all sorts of ideas, from developing survey systems to identify asteroids from space. And you might imagine that that kind of technology that you can detect small asteroids at large distances in space could also be very useful for something like space situational awareness, detecting rogue satellites. We have our asteroid mining technology. And they also develop what they call their Omnivore spacecraft propulsion engines. And the Omnivore engines, as the name might suggest, can use almost any kind of fuel. Omnivore, like an omnivore human being, eats almost anything. And in particular, it can use water, direct water, as fuel for spacecraft. And it's actually a steam-powered spacecraft engine, which I think is really cool that we're going back to the days of steam-powered railway and steam-powered cars. So now we're using steam to power spacecraft. And not only that, but they have their own spacecraft bus here that is powered by their Omnivore engine. So what we want to do is we want to get water from the moon or from asteroids, use the water to fuel the spacecraft, which we then sell to customers that use our bus to move spacecraft in space. So let me give you some background about asteroids and asteroid mining before we move on to the technical details. To create an industry, you need to have somebody who's willing to be a customer. And I think that I'm very disappointed as I've gotten more into this. I was trained as a scientist, and I didn't think about business at all. But it's pretty obvious that if you want to start a business, you need customers. And I think that the government, NASA, really dropped the ball over the past 50 years by not creating an industry. I was at a meeting a few years ago, maybe 8-10 years ago, where United Launch Alliance, which is a company, it's a multi-billion-dollar company with many thousands of employees. It's made hundreds of successful launches, but you've probably never heard of them. It's a combination or a partnership between Boeing and Lockheed Martin. They're a very successful company. They were at this meeting, and they're interested in space industry, and they made an offer to jumpstart the space industry. They said that they would pay $10,000 per liter of water, as long as that liter of water was in high Earth orbit. Because at that time, that was pre-SpaceX, to get a liter of water into high Earth orbit cost more than $10,000. So if somebody else could get it to them and sell it to them for $10,000, they were making money. So I just love that idea. They're creating an economy. They're creating a price point for all of our asteroid mining companies to develop our industry. So water is gold in space. Right? 1 liter of water, this is the bottle of Menehune water, it's common in Hawaii. 1 liter is now worth $10,000 as long as that liter of water is in high Earth orbit. Why water? Well, water is fuel. I just described the Omnivore spacecraft engine, which uses water as fuel, but it can use any volatile at all. Anything that volatilizes when you heat it up can become fuel for the Omnivore engine. So water, you can just pump the water in it directly, and it will work. If we heat it up to very high temperatures, it spits out the back of the engine and moves the spacecraft forward, of course. But water, of course, is also the best possible rocket fuel. If you split it up into its constituent hydrogen and oxygen, it becomes the best possible rocket fuel, and that just requires another step in the process. Water is also great radiation shielding. Water is a really great radiation shield, and it's lighter than, say, steel, and it's more easily formed than steel. So if you want to create a space station that's radiation shielded, and you want to do it out of steel, you have to manufacture it, or you have to build it, you have to do something to it in space or on the ground. But with water, all you do is you create a very thin shell, you pump the water into it as a liquid, it freezes, and then it becomes a easily shaped radiation shield. Very, very, very easy process. Of course, we need it for human consumption and agriculture. And the other process, and I think this is the key, and this is what sort of turned me around when I first heard Joel Sersall, the CEO of the TransAstra company, giving his presentations. This is the first thing that turned me around to actually thinking this could be doable in my lifetime, really soon if we have enough money and venture capital funding to do it. The process is not complicated. It's difficult, but it's not complicated. And he really had, I thought, a very straightforward ideas about how a business model that I could really picture. All the other asteroid mining companies I'd ever heard of that I read about since I was a teenager, they all just seemed ridiculously complicated, and they weren't going to happen for 100 years. But TransAstra has this idea for straightforward asteroid mining. So Joel met me at a conference. In fact, the first time we ever met, we happened to be giving back-to-back lectures and really liked each other's talks. And so he talked to me afterwards, and he said he's starting up this asteroid mining company, and he posed this question to me. He said, how many 5 to 10 meter diameter, water-rich, in-space resource utilization targets are there as a function of return trip delta V? Now, don't worry if you don't understand all the terms in that, in that sentence, okay? Because that's the point of this talk. I'm going to explain now what all that means, because I'm going to answer this question in this talk. So to do that, I need to go give you some background. And I think there's a really great analogy between asteroid mining and gold gold prospecting. Now, I've actually done gold prospecting. I lived in Arizona for 10 years. I had a friend who, we literally went out gold panning in a river, and I actually collected gold. So I know a little bit about what I'm talking about, but I'm certainly no expert and never made a hobby out of it. The photo here is of Sutter's gold mine, and you will notice later on that we use the term Sutter a lot. We use Sutter to refer to our asteroid survey system, and it's named after this mill. This water mill, and notice water plays a key role in this talk as well. This water mill is famous for being the place where gold was discovered in California and starting the California gold rush. So it started the entire economy, built California, and so we've named our asteroid survey system the Sutter survey system in the hopes that our surveying will find water that will start a water rush into space and create a space economy. But of course, you have to be a smart prospector. You have to prepare yourself before going out. You don't just walk down any place in the desert and start gold panning. You don't just start a business without having a business model, without doing a study to see whether or not you can actually be profitable. So you have to know something about what you're doing. So for gold mining, we'll use the process of gold mining, or gold extraction, to illustrate what we do with asteroid mining. So if you want to try and find gold in a river, the most rich spot to mine will be the primary lode. This is where volcanic processes have brought gold, usually intertwined with quartz, from the inner earth and through magma processes up to the surface and is exposed. And there you can go and you can you can chop off nuggets of gold and become very rich very, very quickly without much effort. But around that primary gold, there will be erosion due to wind, due to rain, due to just motion of rocks next to it. And so eventually that primary lode of gold spreads out around the primary lode. And now you've got sort of nuggets lying on the ground, perhaps buried a bit, and you can go around and pick them up. But now they're exposed over a wider area. It takes a little bit more technology to extract the gold. Then eventually that gold can, through water action or wind action or just gravity, find its way down into a river. And so you get this process called alluvial gold. And then once the gold is in the water, it begins to flow. Now gold is a very heavy element. It's a very heavy metal. So it tends to settle fast. And only when the water is flowing fast is the water fast enough to pick up that heavy gold and transport it. But even when it's getting transported, it goes over, say, a waterfall like this into a plunge pool. At the bottom of the plunge pool, there'll be a deep hole that has been gouged out by the water falling. And there you get this chaotic turbulence in the water. And so the heavy gold, as it's floating around, as it's twirling around, the heavy gold just tends to the bottom and then it sinks out. So it collects there at the bottom of this plunge pool. So later on, when geology changes or the river dries up, the gold can be concentrated at the base of where there was this pool. So if you find where these places used to be, you can go there and mine the gold, and there can be very rich deposits of gold in those locations. And finally, the water, smaller pieces of gold, can be transported all the way down the river, especially during heavy floods. And then it's very easy to pick these nuggets of gold up or little flakes of gold on the beaches. You can go by with a pan, and you can pan for gold. This is kind of the thing that I did in Arizona. And you can definitely find gold in these locations. So there's a natural size sorting that occurs throughout this entire process. At the primary lode, you have the very largest nuggets. They're coming out right straight out of the ground. But by the time you find the flakes of gold on the beach, those have to be the smallest flakes because they've been transported all that distance and they have to be moved by water. So there are analogies to every single one of those processes with asteroid mining, which I will get to later. So I just talked about where you find gold on Earth, but what about finding water in the solar system? Now, when I was a teenager, I was very enthusiastic about astronomy, and I wanted to be an astronomer. In fact, I wanted to be an astronomer in Hawaii, and now I am one. And but I wish I could tell you that I had some grand plan that I followed, that took me directly there. But that's completely wrong. It was just blind luck, random walk almost, that got me there, and I just happened to have ended up doing the thing that I wanted to do when I was a teenager. But when I was a teenager, there was a lot of speculation in the books that I read about where you find water in the solar system. And there were some ideas that probably there's water on the poles of Mars. We knew, of course, there's water on Earth. But it really wasn't clear how much water there was elsewhere in our solar system. But it turns out now we know that water is ubiquitous. Water is everywhere. And in fact, water is on the moon. There's lots of water on the moon, in fact. The water on the moon is in polar craters at the north and south pole of the moon. And at the bottom of these craters, it is so dark because the sun has never shone inside these craters for more than 1 billion years. Inside the bottom of these craters at the north and south pole of the moon are colder than the surface of Pluto. They're the coldest places in the solar system, even though they're really close to the Earth. And so any kind of water molecules that ever happened to fall on the moon eventually bounced around on the surface, bounced around until they eventually found themselves at the bottom of these craters. And as soon as they're at the bottom of these craters, it freezes immediately onto all the other ice that's already accumulated there. It's what we call a cold trap. And keep that in mind because it comes into play later on when I talk about how we're going to mine the water. So water is everywhere in our solar system. And in fact, there's lots of water in asteroids. This is another place where we didn't know if there was water until recently. This is the largest asteroid in the main belt. The main belt of asteroids is between Mars and Jupiter. It's the largest asteroid, and we sent a spacecraft there that orbited it for a year and took lots of detailed measurements. And we're pretty sure that about 25% of the mass of Ceres is in water. Now, if that's true, Ceres has more water than Earth. So when you think about, where do you find water and how much water is out there, Ceres, arguably the one largest asteroid in the solar system, has more water than Earth. So if we could get there and mine that water, we'd have an endless supply of water. We have a lot of water there. Now on Ceres it's a little bit more difficult because it's buried underneath a lot of rock and dirt. But we do a lot of drilling on Earth, and you can probably do drilling on Ceres as well to get down to that water. So it could be very economically profitable, and you could support a lot of human habitation there. So where do those asteroids come from? And what are the ones that we're most interested in? So this is an image or a representation of the solar system showing the sun in the center here in yellow, the orbits of the planets. Probably most of you have seen things like this. The Earth is the blue circle right here. Mars is this red circle. Jupiter is this outer circle here. And all the little yellow dots represent known asteroids at the time on one particular day. There are about 1 million known asteroids in this main belt of asteroids here. In this main belt, there are about 1 million asteroids larger than 1 kilometer in diameter. That's about half a mile. So 1 million asteroids larger than half a mile in diameter in that main belt. And it's all between Mars and Jupiter. All these little white arrows here represent known comets at the time that this representation was made. So you can see some comets here are close to the sun. You also notice that some of these little yellow dots that represent asteroids are actually around Earth's orbit. These are what we call the near-Earth objects. And those objects get there because of what we call gravitational interactions. They're called resonances, which are due to mostly Jupiter. So Jupiter is a very massive planet. It's out here, and Jupiter, as it goes around, it pulls on the asteroids in the main belt. And in pulling on the asteroids in the main belt, it pulls the asteroids towards Jupiter. But in coming towards Jupiter, they kind of react, and they also go in towards the inner solar system. So it creates this sort of expanding orbit for these asteroids. So whereas they used to be on nice circular orbits going around the sun between Mars and Jupiter, now they go out to the orbit of Mars, out to the orbit of Jupiter, and also into the orbit of Earth. So these now become what we call near-Earth objects, or the NEO zone, the near-Earth object zone. And these NEOs, these are the ones that we are interested in. A NEO is any object that approaches to within 1.3 astronomical units of the sun. What's an astronomical unit? An astronomical unit is the average distance between the sun and Earth. And it corresponds to about 100 million miles. So anything that can come within 130 million miles of the sun is called a near-Earth object. Now, I think it's actually a really bad name because near-Earth, to me, would imply that it's near Earth. But in fact, most of them are not near Earth, and most of them never come near Earth. It's just, this is our definition. Anything that comes within 130 million miles of the sun is a near-Earth object. But you can see that many of these things, some of them look like they're near Earth here, but many of them are over here, and many of them are over here and over here. And in fact, some of the near-Earth objects are out in the main belt, and they just will eventually come in to the Earth. So it's not really a good name. It's just what we call them. But anyhow, they are the ones that have the potential to come near Earth, but they don't always come near Earth. This is an image, actually a movie, of a near-Earth object that was acquired by a Japanese spacecraft called the Hayabusa that went into orbit around the asteroid Itokawa for about a year or so. And when people got there, they were a little surprised at how it looks like a rubble pile. A lot of people, when I was growing up, they thought that asteroids are just big rocks. And then as I got into the field about 20, 30 years ago, we began to realize that asteroids are, in fact, more like rubble piles. Just imagine a big mountain that's been eroded away, created a pile of rubble at the base of the mountain, and then it's held together very loosely by gravity and by just mechanical forces between the rubble. So that's what we have to deal with now. Now, this is an asteroid. I always like to give people a sense of scale on these things. So that is the space station in proper scale compared to asteroid Itokawa. Itokawa is not an asteroid that contains water. It's a very dry asteroid. But I imagine that there's many people here who don't have any idea about the scale of the space station. So I will also show it relative to a football field. So you can see that a football field, the space station, is about, in total area, the size of a football field. And asteroid Itokawa is, say, a few football fields, five or so football fields in length and about 2 or 3 football fields in diameter. So this is actually a relatively small asteroid, but it is a near-Earth asteroid that can come within 130 million miles of the sun. How many are there in total of these objects? So this is a compilation of some work that I did with and other people's works, giving some idea of how many asteroids there are as a function of their size. It doesn't matter too much. The absolute magnitude here is just size, and I'll give the size values in just a minute. This is a logarithmic scale in the cumulative number of objects, so the cumulative number of objects that are larger than the given size. So at 1 kilometer diameter, corresponding to absolute magnitude 18, there are about 1,000 near-Earth objects. But as you go smaller, because it's a logarithmic scale, the numbers go up very rapidly. At 100 meters in diameter, there's about 100,000 near-Earth objects. And 100 meters diameter is kind of interesting because at 100 meters diameter, that's sort of the minimum size asteroid where if it was to strike the Earth, could puncture through the atmosphere and cause massive damage, sort of on the scale of wiping out Texas. So a 100-meter diameter asteroid could cause a lot of damage, and there's 100,000 of them in near-Earth object space. But that's not the ones we're interested in for our mining project. For our mining project, we're interested in objects that are sort of 10 meters in diameter. Say the size of this room. Think of an asteroid the size of this room, maybe a little smaller in this size range. And at that size range, it gets really difficult to know how many there are because they're really hard to find. They're very small, and it's really hard to know when you see 5 of them to know that there's 100 billion of them. A billion of them is a difficult calculation to make. But anyhow, our best calculations suggest that at sort of the 10-meter diameter scale, there's somewhere between 100 million and a billion objects on the 10-meter diameter, larger than the 10-meter diameter scale. So there's lots of things about asteroids if you want to mine them and make money off of them. It's like real estate. It's all about location, location, location. With asteroids, it's also about location, location, location. It turns out that but I just said that there's 100 million to a billion near-Earth objects in the 10-meter diameter scale range. There is one 10-meter diameter near-Earth object closer than the moon at all times. So right now, there's an asteroid the size of this room, say, closer to us than the moon is. So they're there. There's lots of them. The problem is that not all of them are equally accessible. So the accessibility is determined by something we call delta V. Delta stands for change, V is velocity. So delta V means the change in velocity that's required to get to or from an object. And what we're really concerned about is the delta V, the change in velocity required to get from the asteroid back to Earth. We don't care how much delta V it takes to get to the asteroid, because then we're just going out with our spacecraft. When we're coming back with 100 tons of water. And so it's a lot harder to move 100 tons of water than it is to move a 2-ton spacecraft. So we're really worried about the delta V coming back from the space from after mining. So delta
12,
V,
11, 10, 9, 8, 7, Start. 2, 1.
Delta V is the amount of energy it takes in your rocket engines, right? It takes energy in your launch vehicles and your rocket engines to change your velocity. And that's what we're concerned about. And we measure the amount of energy it takes in terms of this thing we call delta V. So this is a figure from a paper from 8 years ago, one of my illustrious colleagues. And he did this sort of a calculation or study, a presentation of what kind of asteroids we know about and how much energy, delta V, it takes to get places. So it's the amount of energy in delta V versus the round-trip mission duration time. And I don't like this. You know, I hate it when I read the financial papers and they show the Dow Jones, but they do it with a suppressed zero. So I like to show real zeros on my figures. And 0 is the Earth's surface. So it doesn't take any energy to get from the Earth's surface to the Earth's surface, right? You know, that's not much delta V, and I come back to the Earth's surface. So the Earth's surface is 0 delta V, but if you want to get from Earth's surface to the International Space Station, and you want to do it as a round trip, you want to get to the space station and back, you need to have enough energy to have sort of 10 kilometers per second change in your velocity. 5 kilometers per second to get up, 5 kilometers per second to get back down. If you want to go to the moon, you need double that. You need about 20 kilometers per second. 10 kilometers per second to get to the moon, 10 kilometers to get back. Now, all these little red, yellow circles you see here represent known asteroids at the time. And so these are the most accessible known near-Earth asteroids at the time that this paper was written in 2014. So you can see that even the most accessible ones from Earth's surface were down to 14 kilometers per second, which is a lot of energy. It's really hard to get that kind of speeds. But a thorough survey, and this is key, I'm going to be talking about our thorough survey, would discover thousands more asteroids to visit and mine in the next 2 decades. And as you get to those objects, as you go mine those objects, we can use them, again, in space. You know, our goal isn't to bring the water back to Earth. That would be stupid. There's lots of water on Earth, unless we could find some really rich people who are willing to pay $20,000 a bottle for a liter. And that's not crazy, okay? We looked up how much people will pay for fancy water, there's a business. If anybody wants to talk to us about selling asteroid water, please come talk to us. So missions to, if we're up there and we're actually using the water in space, that means we no longer have to come back down to Earth's surface and then leave again. We can start our missions in space and go to other asteroids. We can go to other planets. We can go to other space stations. So we want to use it in space, and that is what we call, that's where our gas station is going to be. It's going to be a very high orbit around the moon. You might have heard of it. It's called the Lunar Gateway, or Artemis. That's what NASA's planning. But that's sort of where our base is going to be in space, where we're going to deliver our water to, like a gas station or a water station. People will come there to get their stuff. But using it in space is what's, keep forgetting. So this talk all deals with asteroids in this kind of a range right here, because we're not talking anymore about going from the Earth to the asteroid. We're talking about going from the Lunar Gateway to the asteroid and back. So we no longer have to worry about coming all the way down into Earth's gravity well. We don't have to go to the moon's gravity well. We're going to be in space on high orbit around the moon, and we're only going to go from the moon, or from that area, to other asteroids that are sort of low delta V. So our maximum delta V that we care about is about 3 kilometers per second. And 3 kilometers per second is important because that's the value at which we bring back half the water that we mine. So if we can find asteroids that we can go to, mine them, and come back, that means we're only going to consume half of the water that we mined as fuel. So we come back with half of our material. So finally, that's what we mean by in situ resource utilization, ISRU. It's the fact in situ means, you know, in place. Resource utilization means we're going to use the resources that we mine in place in space. We're not going to bring it back to Earth. We're not going to bring it back down into the gravity well on the moon. We want to have a space economy. So as I just said, a delta V of 3 kilometers per second returns 50% of the mined water to the Earth-Moon system. So moving on, another thing they need to be concerned about when you're talking about mining asteroids is their size. Size is really important because you have to do something with it. You have to mine it. You have to manipulate it. So for us, we've done some studies to try and determine what the best ISRU target diameter is. At less than 5 meter diameter, so think of something the size of a car, there's just not enough water in them to make them economically viable. It'll cost us more to go out there than it will be than the profit that we bring back. At much greater than 30 meters diameter, we're actually designing ships, mining spacecraft that can handle 30 to 50 meter diameter, but at much bigger than the 30 meters diameter, the things are just too big for the technology that we're developing. It could be that there are other technologies that you can use. It could be that you could pluck a boulder off of a 50-meter diameter asteroid and then work on the boulder and then go pluck another boulder off of it. But that's not what we're designing right now. So for us, the optimal diameter asteroid that we're talking about is 5 to 30 meters in diameter, something on the order of the size of this room. Right? So an asteroid that think of it as big as this room. And I think the final thing that you have to be concerned about when you're talking about what's interesting in an asteroid is taxonomy. Taxonomy is the science of classification. So it's the classification of asteroids that we're talking about. I get so annoyed when scientists show tables like this. So concentrate just on these two columns. There's all sorts of different taxonomies, and astronomers are not particularly imaginative when they come up with names for them. So they were named S, C, and D. By one of my colleagues at the University of Hawaii. S, you can think of it as silicate-like asteroids. So think of sand, and they are the color sand. They contain a lot of olivine. If you've ever been to the green sand beach in Hawaii, the green sand there is olivine, and it's very prevalent on asteroids, olivine and pyroxene. C, you can think of as carbonaceous. And C-type asteroids are very dark, like coal. So carbonaceous coal. Think about coal. Think about how dark coal is. So a C-type asteroid is really kind of coal-like. In fact, if you pick it up and you smell it, it smells like coal. And it's actually kind of toxic. But it also contains some water. The D-type asteroids are really more like what's inside of comets. So a comet is really a D-type asteroid. So it turns out, though, that the D-type asteroids rarely come into the near-Earth object space. The only ones that come into near-Earth object space are the S and Cs. And so of those two, there's only one choice for mining asteroids in near-Earth object space. It has to be these C-type asteroids that are, let's call it between friends, 15% water by mass. So 15% of the mass of a C-type asteroid is water. So those are the ones we're concentrated. And it's very easy to extract them. We have samples of these C-type asteroids on Earth. They fall down to the Earth. It's called, they're first meteors shooting stars. They land on the Earth. They're called meteorites. And when you pick them up off the ground, you can see this. You can smell it. It smells like coal, like I said. And you can put it into a test tube, and you heat it up on a Bunsen burner, and water comes out of it. And this water right here is water out of an asteroid, easily extracted just by heating it up. So that's the basic idea of our strategy. So let's put it all together, all these things I've just told you, and try and get a little bit more science behind it. This is a map of the distribution of asteroid taxonomies through the main belt. Now, I use this term here, semi-major axis. Think of that as roughly the distance from the sun in hundreds of millions of miles. So 200 million, 300 million, 400 million miles from the sun. Remember, the Earth is 100 million miles from the sun. And then this is the amount of mass per unit distance. Let's call it that. So we, of course, are interested in these C-type asteroids. These are the ones that contain water. And it's a little hard to see, so I'm going to help you out here. The C-type asteroids are those lines there, those sort of yellowish lines that are being pointed to by the arrows. And you can sort of see that the C-types, and notice that this is a logarithmic scale. So it doesn't look like maybe there's much difference between, say, the inner edge of the main belt and the outer edge of the main belt. But in fact, there's almost a factor of 100 difference in the amount of mass of C-type asteroids between the inner and outer edges of the main belt. And so the most rich area of the belt is this outer belt, and that's where we hope asteroids from this outer belt will come into the near-Earth object population, because those are the ones we want to mine. We don't care about these S-types that dominate the inner edge because they're dry. So we want asteroids from the outer edge of the main belt to come into the inner solar system. And we want Jupiter's gravity. Jupiter's gravity is the thing that pushes them into the inner solar system. So we're using Jupiter to help us mine these asteroids. Here's another figure that shows the distribution in two dimensions. So that, again, is roughly the distance from the sun in hundreds of millions of miles. And the inclination is something called, it's the tilt of the Earth, of the asteroid's orbit relative to the Earth's orbit. So if the Earth is orbiting the sun in a plane, then the asteroid orbits in this plane. It's that angle that is the angle between, that I'm talking about here. And you notice something really interesting. It's very obvious that the asteroids are not distributed randomly throughout the belt. There are gaps everywhere. And there's also clumps of things. So what explains these gaps and these clumps? So those clumps are due to asteroid collisions. Asteroids, there's something, like I said, there's 1 million asteroids larger than half a mile diameter in the main belt, and they collide. They don't collide every day, but they collide every million years. And when they collide, they create a bunch of fragments. And those fragments then spread out in time due to gravitational effects of Jupiter and other factors we'll talk about. So anytime you see a big clump here, those clumps are all due to an asteroid, two asteroids colliding millions to hundreds of millions of years ago in the main belt. So what it's doing is it's releasing all that material, opening it up. So it's basically cracking the rock open for us. And then you notice these gaps, these vertical gaps here, they're called mean motion resonances. That's where Jupiter is pumping the asteroids into near-Earth object space. This one here is shown as the 5-to-2, which since it's labeled, I'll talk about it. What that means is that the asteroid makes 5 revolutions around the sun for every 2 revolutions around the sun that Jupiter does. And so that means that every time that happens, the asteroid and the Jupiter are now in exactly the same location. Now imagine if you're pushing a child on a swing, and we've all done this, I know. You can just have like one finger, and you can just tap the child. And as long as you tap the child at exactly the same frequency, it doesn't matter how hard you're tapping them, eventually the child's going to build up a gigantic swing, and they're going to move a long distance. And it's the same thing with Jupiter. If every 5 revolutions of Jupiter around the sun, Jupiter taps that asteroid, pulls on it, it's going to change that asteroid's orbit. And that's exactly what's happening here, is that Jupiter clears out any asteroid that happens to be in that region. And it sends most of them into the near-Earth object space. So Jupiter then is like the truck that's picking up all the rubble and bringing it to Earth for us. And finally, there's this other subtle effect, which I'm not going to go into too much detail, but it's called Yarkovsky drift. It was discovered by a Russian physicist 60, 70 years ago, and completely ignored for 50 years, and then it sort of came back when we realized how important it is. And it's due to a subtle thermal effect about that's a size-dependent thermal effect that can make asteroids move either outwards from the sun or inwards from the sun, depending on which way they're rotating. Asteroids that rotate one direction move in, asteroids that rotate the other direction move out, and it's size dependent. The smaller the asteroid, the faster they move. So any asteroid, even if an asteroid is not in this mean motion resonance right now, if it's close to it, and the asteroid is small enough, eventually those asteroids are going to move into that mean motion resonance, and then they are going to get sent off into the near-Earth object space. So we have this constant feeding mechanism into the inner solar system of the asteroids that we want to mine. And this is a map now showing where the asteroids that actually are in near-Earth object space are located. And you can see that all the ones that are located in near-Earth object space are all on these mean motion resonances. So all these asteroids here are there because of the Yarkovsky effect and Jupiter pushing those asteroids towards the Earth. So a long time ago, 20 years ago, I got involved in this research, and we were studying, and we were actually trying to quantify where in the main belt do near-Earth objects come from. And I'm not going to go into too much detail on this. I just want you to get the basic idea. But we divided the main belt of asteroids up into 7 different sources, and based mostly on their distance from the sun. And we gave them names, their common names, to astronomers. So the Hungaria asteroids in the main belt leave a fingerprint. And you don't need to know what this is, but just look at it as sort of like a fingerprint. The Hungaria asteroids in the main belt leave a fingerprint of what their distribution is within the near-Earth object's distribution of their orbit elements. And this is the fingerprint of Hungaria's. And if we show the other 6 types of objects that come from the main belt, this is their fingerprints. Now, to you, looking out there, looking at it quickly, they may all look the same. But in fact, if you look at it in some detail, you'll realize that these clumps here all move. They're all moving. So they're all in different locations, which means that each one of the different sources of near-Earth objects in the main belt contributes in a different way to the near-Earth object population. It leaves its own fingerprint. So now we can actually use this to predict which objects or how many objects come from each region in the main belt. And now remember I showed you how the number of C-type asteroids, the ones that bear water, are more common in the outer belt. So we know that these sources here are in the outer belt. These sources here are in the inner belt. So now we can actually map out how many of the C-type asteroids are coming from the outer belt into the near-Earth object space. So now I can actually answer the question that was posed to me. How many 5 to 10 meter diameter water-rich ISRU targets are there as a function of return trip delta V? Now I hope you all understand that question now. So now I'm able to answer this question for Joel Sercel, the TransAstra CEO. And this is the answer. He spent a lot of money, a lot of time getting this figure out of me. And so here, now you recognize delta V. You recognize, okay, so what we're really concerned about because of the size considerations is that we want asteroids greater than 4 meters in diameter. 4 or 5, it doesn't matter too much. The solid line represents all asteroids that are smaller, that have a delta V smaller than the value on the x-axis. So what we're concerned about, again, is the 3 kilometers per second. 3 kilometers per second means that we return 50% of the water that we mined. So if we have an asteroid that's less than 3 kilometers per second, we return more than 50%. An asteroid at more than 3 kilometers per second, we return less than 50% of the water that we mined. So these are the economically profitable ones at this time. And the number is about 1,000. There's about 1,000 asteroids that we think are good ISRU targets. 1,000 low delta V asteroid mining candidates are out there. And these objects have got very particular properties. They all are on very Earth-like orbits. This is a representation. The red circle represents the Earth's orbit. The blue arrow over here represents the Earth and its direction of motion at that point. And the sun would be right here at 0, 0. And all these black arrows represent the location and velocity vector of the asteroids that are asteroid mining candidates. So you can see they're all very Earth-like asteroids. So if you account for all the different sizes of those 1,000 asteroids, and you assume that 15%, as we said, of the C-type asteroids are water by mass, that means that there's 100,000 tons of water in those 1,000 asteroids. And then, if you multiply it by the amount of money that United Launch Alliance was willing to pay for a liter of water, that turns out to be $1 trillion. Okay? So now we have our $1 trillion industry for the 21st century. Now let's go back and look at the parallels between gold mining and asteroid mining. Again, we want to be smart. We don't want to just go out without a business plan. We don't want to just go to an asteroid that's dry. We want to find asteroids that are wet. And when I say wet, I should point out that it's not that they have pools of water buried inside of them. It's not like there's a chunk of ice inside of them. That's not there. What I mean wet is that the water has been incorporated, the molecular water has been incorporated into the mineralogical matrix of the asteroid. So it's just water molecules here and there. But it means that roughly 1 in 8 molecules on the asteroid are water molecules. And so you just got to find a way to get them out. So we want to find those asteroids. So with asteroids, the mother lode is the actual primary asteroid that's out in the asteroid belt. The residual gold is the asteroid fragments that came off of the collision of the 2 asteroids in the main belt. The plunge pool corresponds to those stable resonances, those resonances that are causing, with Jupiter, that are causing the asteroids to leave the main belt and come into the near-Earth object space. And the river deltas and beaches corresponds to the inner solar system. That's where we are. So we're down at the very end of the line, and the solar system is doing the work, the hard work of feeding all these asteroids to us, and we're just going to walk down along the beach around Earth's orbit, and we're going to scoop up all the water of the asteroids, just like you can walk down the beach and scoop up gold out of the sand. And with gold, there's this natural size sorting that occurs due to the weight of gold and the fact that water is able to move smaller pieces of gold, flakes of gold further. But that also happens with the solar system because of this Yarkovsky effect I told you about. The Yarkovsky effect is size dependent. Smaller asteroids move faster and they move further than big asteroids. So there's a nice parallel between all the gold mining and all the water mining that we want to do. So how will TransAstra actually mine water from asteroids? I'm going to go over it sort of slide by slide first, and then I will show you a movie sort of putting it all together. So our idea is to use concentrated sunlight. I showed that you could just heat up an asteroid and you can get dry water out of it. So if you've got this representation here of asteroid regolith, in other words, asteroid surface, you have concentrated sunlight shining on it. Well, it's going to heat up the surface. You heat up the surface of the asteroid, what happens, just like anything, the surface expands, and there's going to be shear forces inside of it. But then there's going to be volatiles that are inside the asteroid that are going to heat up, and the surface is going to fracture, and then the volatiles that are inside the surface, those water molecules, are going to blow off the particles that just fractured off the surface. And now all of a sudden you've cleared out more surface, more fresh surface that this concentrated sunlight's still shining on, and you can repeat that process. So we got this whole movie here, which shows this whole process quickly. So you got concentrated sunlight, heating up the surface, fracturing the surface, and then it gets blown off by the sublimation of the particles inside, and then you repeat this process. And so you can dig a hole into the asteroid just using concentrated sunlight. So we've actually shown this in the laboratory. Sometimes the laboratory we're using is big. This is the White Sands Missile Range Solar Furnace in New Mexico. And it's a gigantic solar furnace that can reach temperatures of 6,000 degrees Fahrenheit, which is sort of the temperatures that we're talking about reaching with our asteroid mining process. And we put a chunk of rock at the focus of this solar furnace. The chunk of rock is an earth rock, but it's an earth rock that's kind of a proxy for the kind of material that we expect to find on asteroid surfaces. And this is what happened. Oh. It shows it playing, but it's not actually doing anything. Okay, I'll show you what happens in the laboratory. So this is instead of being at the big solar furnace in New Mexico, this is in a laboratory at the Colorado School of Mines. And what we've done is we're using the world's brightest light bulb. It's the brightest light bulb that you can buy commercially. And we focus it down onto the surface of an asteroid simulant. This asteroid simulant is created by a group at the University of Central Florida. They make simulants of all sorts of surfaces, extraterrestrial surfaces, like the moon, like asteroids, like Mars. So we bought this simulant from them. We put it into a vacuum. We have our brightest light bulb in the world focused onto the surface. And you can see it does exactly like what our little cartoon image did. And well, yeah, exactly like what our cartoon image did. We're basically digging a hole. And if we let this go on, and then I could show you what happened afterwards, we just dug a hole into this asteroid simulant. Just so it works, at least in the laboratory, our technique seems to work just fine. So we want to put this into a what we call the honeybee system. We have an asteroid that we bag up, and we have gigantic inflatable mirrors that collect light, pump it down into a light tube, and then the light tube, and on both sides here, there's a big mirror over here too, pumps it down, the light gets focused onto the surface of the asteroid. We dig into it using this optical mining concept. The water vapor gets into this bag. Once it's in the bag, it sort of finds its way through these tubes into these balls. These balls never see sunlight, so they become very cold, and they become a cold trap, just like the inner surfaces of the craters at the south and north pole of the moon. They're cold traps. Water freezes in them. So we collect our water here, and then eventually, once we've entirely sucked all the water out of this asteroid, we disconnect, we spit the asteroid out, and we take our water back to our customers. And it's important to remember that we're not baking the whole asteroid. It's not like we put the whole asteroid into a microwave, hit 90 days, and the water comes out. We're actually spalling it. We're digging into the asteroid using this optical mining process. Now you may think that gigantic inflatable mirrors in space sounds insane, but in fact, 30 years ago, NASA built and tested inflatable mirrors in space, and they were successful. They're not hard to operate, as long as you're not trying to use them to actually to create images of distant stars or galaxies. All you want to do is collect light and focus it down. They work just fine. And so this is a 14-meter diameter inflatable reflector built by NASA 30 years ago. The technology has improved since then. We can do this. This is not new technology. And in fact, we are doing this. We are building right now the world's first asteroid mining spacecraft. And it's not just CAD drawing. We are actually building it. It is in a laboratory in Los Angeles. This is the one we're building right now. We call it a Mini B. All the names are all B related. And because we're going to collect material from different asteroids. And we have inflatable mirrors. Basically, everything that you see here is being built, and is not being built just for testing in the lab. It's being built with the intent to fly it. We have the intent to fly it. It is built to be flight ready. We just need to get the $1 million or so to actually launch it somehow, and we're hoping to find some venture capitalists that will do that. And it is under construction now. One of the interesting things. One of the interesting things is the mechanism to get the bag. We use inflatable arms, like we use inflatable mirrors. And this is a ground demonstration of the inflatable system. Now remember, in space, it doesn't have to work against gravity, so it'll be much easier, much faster. This is sped up, so it expands. We use this, in this case, it's just some sort of a beach ball that we drop down into the bag. The bag then closes up. This is all done with hydraulics. And then we have a robotic zipper that zips it up to create a hermetic seal. And once it is hermetically sealed, then we also use struts. We can deflate the bag, and we can use motor-driven straps to basically drag the asteroid down against the lens that we then focus light onto it. So this actually works. This is not CGI. This is real there. And now I know some of you are thinking, well, if we're going to launch our little miniature spacecraft, don't you need a miniature asteroid? And how do you find a miniature asteroid? Well, we've built our own miniature asteroid. We've built this asteroid. It's about the size of a beach ball. And we are, again, using this synthetic asteroid material from this group at the University of Central Florida that makes, as realistic as possible, Asteroid Simulant. And of course, we're using Asteroid Simulant that represents this C-type asteroid that's got 15% water in it by mass. And so the idea is that we will launch the Mini B and the synthetic asteroid at the same time, the same launch vehicle. We'll spit them both out of the launch vehicle. The Mini B spacecraft will search around for the synthetic asteroid, and then it'll go and it'll mine this asteroid. And we know exactly how much water we put into that thing, and so we can measure how efficient our spacecraft is at extracting the water from that synthetic asteroid. And this is a demonstration of the tracking system. This is sort of one solar panel with the spacecraft bus in the middle. You've got a screen here showing what the camera is seeing inside the spacecraft. And the point of this demonstration is to show that we can very easily have the spacecraft automatically point and stay focused and on the sun. And it can just do it all automatically, tracking without any human being having to be there with a joystick. We've got a whole bunch of optical testing going on. This is some sort of recent test showing laser optical test to verify that we can deploy the mirrors and have them come to a focus. Now remember, all we need is for the focus to concentrate all the light to within maybe a 10 centimeter, 3-inch diameter circle, as it does right over here. So all the light comes to a focus there. So if you got all the light from the sun over a 14-meter diameter mirror concentrated into something this big, you get 3,000, 4,000 degrees and enough to drive the water up. Cool. So the next process is discovering the targets. And there's a big system being developed right now in Chile called the Large Synoptic Survey Telescope, which has got a gigantic 8-meter diameter mirror, and it has the world's biggest camera with 10 billion pixels on it. And but we don't think it's going to be very good for finding the asteroids we're interested in. So we're developing our own Sutter survey system, named after the gold mill or the sawmill in California. This is an artist's conception of our system in Arizona. In fact, Tomorrow, I'm flying to Arizona to help install this system. This is not just CGI. This is actually really happening. And we're installing the system here, and we're going to demonstrate on the ground our technology that we're going to be using to find asteroids in space. This would be, and then once we demonstrate that we can do it on the ground, we're going to build a system that we will put in low Earth orbit, demonstrate that we can do the same thing in low Earth orbit. And then our plan is to create at least three, what we call Sutter Ultra systems that each have 109 12-inch, 30-centimeter diameter telescopes. And we are going to put them on a special orbit, which I will tell you about soon. And each one, we can fit 3 of those into a Falcon 9 launch vehicle. So we can launch all 3 at the same time. It's all been designed to fit into one of these launch vehicles. And then we're going to launch them not into orbit around Earth. We're going to launch them into orbit around the sun. But they're on very carefully chosen orbits around the sun so that they appear to be going around the Earth at very large distances. So, and I will get to that in just a second. So these spacecraft will be going around the sun, but we sort of draw this purple circle here to represent the fact that they're sort of apparently going around the Earth. And we will just survey for asteroids in that volume where they tend to be. So here's our final mission concept. I hope this comes through in this lighting. What we have here is the Earth, and the Moon is going around the Earth as well. We have the 3 spacecraft here. The little blue circles that you see here represent synthetic ISRU mining targets. Okay, so we know that all those targets are in near Earth orbit, right? I showed that they all have very Earth-like orbits, and we've got our spacecraft here. And remember, the spacecraft are actually going around the sun. So even though they're going around the sun, it looks like they're going around the Earth. And I don't want to go into the dynamics there, what's going on, but it looks like they're going around the Earth. And not only that, they're going around the Earth embedded within this sort of donut of the interesting asteroid targets that we're concerned about. So we want to maximize our ability to identify these asteroids. We've got a whole bunch of other technology that's going on there. So the concept is that we've got, we don't want to find an asteroid and then go build the spacecraft like NASA does and then go after the asteroid. We want to have our mining spacecraft already in high Earth orbit so that when we find an asteroid, we're ready to go for it right away. So we have our mining spacecraft in high Earth orbit, and then one of our spacecraft detects an interesting asteroid, in this case, this one right here. And the arrows here represent the direction of the Earth and the direction of the asteroid. And then since the Earth is closer to the sun is down here. Since the Earth is closer to the sun, it's moving faster than the asteroid. So one of our spacecraft finds an interesting asteroid. It says, oh, wow, that looks interesting. So then once we think it's interesting, then we can target it with our other spacecraft. And now we've got great triangulation on it, so we can get a really good orbit on it. And if we're really lucky, we can get it from the Earth, maybe bounce a radar beam off it or something. And so we can get a really, really good orbit. Once we have a good orbit and we've measured its other properties, then we launch the APIS mining system. And we think we can launch within about 14 days of discovery. We think it takes us about 14 days to characterize the asteroid well enough that we can actually decide that this is a viable mining target. We go to the target. We spend sort of on the order of 90 days, maybe 90 to 180 days, mining the target, extracting the water. And then we return to the Earth-Moon system, and we deliver water to customers in cislunar space and make a lot of money. At least that's the plan. So we think, doing our calculations right now, that, and this accounts for a lot of different things, like how many asteroids we can actually detect per year, how many missions we can run. We think we could run 2 missions per year that would return a total of 100 tons of water per year to high Earth orbit, or to our gateway system around the Moon. Now, the scientist in me has to give you an uncertainty on that number, and the uncertainty is 100%. So we could get. I love the way you think. Yeah, we could get 200 tons a year, but there's the universe doesn't normally conspire like that. The universe normally tries to drive you down to lower values. But anyhow, this is doing an honest calculation as well as we can, given what we know, 100 tons of water per year to the system. So I know you're all sitting there and probably you're all thinking, this is just a really crazy idea, right? I would have thought the same thing 10 years ago until I had actually heard all of it coming together and been involved in it. And it seems to me that of all the crazy ideas out there, it is one of the ones that might actually work. We get our funding from a program at NASA called the NASA Innovative Advanced Concepts Program, NIAC. And NIAC does what I think everybody thinks NASA does. Because most of NASA programs are very conservative. That's why SpaceX is blowing away NASA. Because NASA is extremely conservative. They don't do things that are on the edge. NIAC does things that are on the edge. So that's why we get our funding from NIAC. NIAC saw that we actually had a viable idea, and they were providing us funding to develop our technologies. And I think that we were the very first group ever to get the phase 3 funding from NIAC, which basically means that we've proven to them that we are actually worthwhile, and we are the first group ever to get their phase 3 funding. So, but I also like to contrast it with, if you were sitting in a lecture room 100 years ago, and I had been some oil mining industry person who said, oh yeah, I'm going to build these massive facilities that are going to mine water in the middle of the ocean through hurricanes, and I'm going to drill down through 2 miles of water and then drill down 2 miles into the crust at an angle, and I'm going to extract oil from that, and I'm going to keep this whole thing steady to within 20 centimeters. You would have thought they were crazy. And the same thing, if you were going to develop an exploration ship, right, which is just a relatively small ship, that you were going to be drilling multiple holes like this, always at different angles, at different ways, all over the world. And these things cost hundreds of millions to billions of dollars. And you would have thought these are just crazy. This guy's just nuts, and you would never want to support it. So what we do is we need to have people who are willing to dream and to do the things that will hopefully seem perfectly normal in 50 years. And I hope maybe that some of you can be involved in that. So acknowledgments, like normal, I think I call it NIAC first because if it wasn't for them, we wouldn't have been able to get our project started. Now we have a whole bunch of venture capitalists, and I think we have 20 people working on the payroll right now. So in summary, there's unlikely to be large asteroids at acceptable delta V. So we focus on the decameter scale projects, targets, the things about this size. We think that there's about 100,000 tons of water within a few kilometers per second of Earth, and as I said, that's worth about $1 trillion. The Sutter Ultra Survey will prospect for mining targets using space-based multi-telescope systems. The APIS optical mining technology, trademarked, excavates and extracts volatiles without any mechanical digging. It's the system where we focus the light onto the asteroid, and just the volatile material inside the asteroid blows the material off. And the most important thing about this whole talk is that I think right now you are standing in front of, or sitting in front of, who will be the world's first billionaire astronomer. So thanks very much.
About 15 minutes or so for questions. We do have a microphone coming around to you since we're live streaming and recording. If you have a question, put your hand up and we'll get a microphone to you. We have a question here.
Okay, this is going through awesome. So first of all, fantastic talk. I'd actually seen the concept for the honeybee earlier. As far as one thing that I am a little bit curious about is, and I understand how this would be difficult to test on Earth, that is how you could get all the asteroid material. I assume that you are slowly counting on the asteroid's rotation, or like the arm moves it, but in that case, if it's a 10 to 5 meter object, that's thousands of tons.
Yeah, so you're talking about once we got the asteroid in the bag, and then how do we move it around so that we can be mining different parts of it?
Yes.
So I'm the astronomer,
Okay.
and so I'm the one who calculates how many there are out there and talks about trajectories to the asteroids and all that. And I asked the same question, and the engineers assure me that they have technology that can do this. And
That sounds like engineers.
well, I love working with engineers because when you work with scientists, the scientists, they're trained. Scientists are trained to attack everything. It's their job to find what's wrong with something. That's how you win Nobel Prizes. But engineers look at a problem and they say, oh yeah, that sounds really cool. I wonder how we can get that working. And that's what they're doing with the asteroids. They think they have technology to sort of manipulate the asteroid. I've seen things like, I forget there's a word for them. It's a known technology that, sort of, it's like tensor bands or something like this, that you sort of create this sort of geodesic structure in banding around the asteroid, and then it can sort of expand. And then when it expands, it rotates a little bit, and then you recontract on it, and then you sort of move it around. And they've got arms to do it. And it seems like it's an interesting technology, but of course it needs to be tested out in space.
Am I allowed to ask another question?
One follow-on.
Okay, understandable. As far as that you've tested with the synthetic asteroid material, is there any concern about other products that might be vaporized? Like, if any of the rock vaporizes and deposits in the bag?
Yes, there's a lot of concern about it. The asteroid simulants that we have are the best asteroid simulants that exist. They're the only asteroid simulants that exist.
Until we have an asteroid here, that's what we've got.
But another problem is that we know that there are things in asteroids that we're not allowed to put into the asteroid simulant because they're toxic. So the University of Central Florida group that does these things, they can't produce a toxic substance that gets then distributed to places. So they've removed all the toxic stuff from it. So we're not really testing on real asteroid simulant, but as good as it can be. And there is also concerns about what happens to all the material that blows off, and where does it go in the bag, and does it clog up the works? So these are all things that need to be worked out. But I remain hopeful, and I think that these are all questions that need to be answered, but I'm trying to think like an engineer and say, yeah, we can get them answered, instead of a scientist, oh, you'll never do that. So.
Hands up for that.
Other question? We have a question right here.
I think I can talk loud enough.
Use the microphone.
Okay. Breaking the rules already.
Yeah.
I have a related question to the first one, and I'm interested about, small asteroids rotate quite fast or tumble. How do you keep the angular momentum from being imparted to the spacecraft when you close that bag?
So the Sutter Ultra Survey System will have 109 telescopes, and I didn't go into too much detail. There clearly wasn't enough time. But we can use that system to measure the rotation rate of the asteroids. And so the first thing we do is we say, so if an asteroid is not rotating, there's no problem. If an asteroid is rotating slowly on one axis, you can imagine that if it's rotating like this, you just have the spacecraft come up along its axis, and then you match the spacecraft rotation to it so that they're both rotating at the same rate, and then there's no problem. So the problem happens when the asteroid is rotating too fast, because then you can't match it and it's too complicated, or if the asteroid is in a tumbling state. If the asteroid is tumbling, then there's no axis that you can come down and actually work on. So we think that the Sutter Ultra Survey System can measure rotation rates, so we can eliminate all the fast rotators. And we need to study whether or not we can determine whether we can detect whether or not they're tumbling. And we think, although we haven't yet tested it, that using the triangulation system from the different spacecraft that we have, so one of the problems with doing this, measuring tumbling from the Earth, is that from the Earth you typically only have one vantage point. But and that vantage point doesn't change very much. But from the two spacecraft, or maybe even three spacecraft, we have different vantage points. And we hope that we will be able to detect whether or not it's tumbling. So if we detect an asteroid that's moving too fast or tumbling, we just don't go to that one. And another answer is that right now, in fact, I'm working with an undergraduate student who we took sort of an unbiased set of images of a few dozen small asteroids of the size range. And now we're actually trying to measure the rotation rates of all of them. And other people have done, there's about 20 rotation rates of asteroids in this size range. But the thing is that there's a bias that goes on, that when people report data like that, typically people only report data where they find a light curve. So they're only ever reporting things where they actually can see the thing rotating. Whereas if you can't see it rotating, that means it's either not rotating or rotating so slowly that it doesn't matter. And so we intend to actually do sort of like a real unbiased study of what the rotation rate distribution is for these small asteroids so we can do a better estimate of how many targets we can viably mine.
Okay, we have a question.
Hey, you gave some really great like historical examples. So, you know, in our human history, we were in our first industrial revolution. We were very wasteful. We were very pollutant. We polluted our world that we know. You know, we're talking about creating big objects into smaller objects and releasing them maybe out into space. You know, as those velocities, as those small particles increase, they can create, you know, potential damages and hazards. Is there any thought to like your industry wide is about like how maybe those pollutants or any kind of negative effects from any of the mining?
Yeah, so, you know, it's a modern world, and so we are very sensitive to the environment. I'd say me more so than my CEO. But no, he's very concerned about it, and he goes to meetings, he talks with lots of people about what can be done. I think that the thing to keep in mind, though, is that you know, people used to say the ocean is big, we'll never pollute it. And so you can say the same thing about space. Space is really big, and so we'll never pollute it. That's probably correct, but maybe naive. I mean, space is much, much bigger than the oceans. The other thing to keep in mind is that if we destroy an asteroid, say a 10-meter diameter asteroid, and do 2 per year, and then we remove our bag and leave basically a bag of dust or a ball of dust that's moving on, that happens naturally all the time. So the reason we have shooting stars, the reason we have meteors in our sky is because asteroids collide with each other all the time. And there's this constant rain of material down on Earth. The mass of the Earth increases, I forget the exact number, but it's something like by 100,000 tons per year. So 100,000 tons of asteroid material rains down on the Earth every single year. And that's just because of the natural collisions between asteroids in our solar system. So if we create 2 new asteroids that are, you know, disrupted, it's a tiny, tiny, tiny contribution to what the solar system's already doing. If you could imagine that maybe if we were on a particular asteroid that had a particularly close approach with Earth, maybe there's something that we could be more worried about. But that's relatively easy to calculate too. So we could just avoid going to any asteroid that we know is going to have a really particularly close approach to Earth anytime in the next 100 years or something.
Just curious, what is the cost of all
You want to switch that on?
Out of curiosity, what is the cost of all this, sending up the 3, well, basically telescopes and 1 digger?
So it depends on which component you're talking about and what version of it you're talking about. So the mini B that we're building right now is a few $1 million. The next version up will be much more expensive, but then again, we benefit from all the experience we have from building the mini B. You know, I would say that the number you can keep in your head for building a spacecraft that might be able to mine an asteroid this size of this room or half the size of this room might be tens of millions of dollars.
All right. Professor?
Oh, go ahead.
Go.
All right. A great talk. Not sure I believe it, but a great talk. I'm trained to say that. But the thing is, you're gathering volatiles, and you've said this toxic nasties in C-type asteroids. How are you going to refine the product so you just get water?
Well, I mean, I understand that on Earth, I think that refining water and removing toxic material is relatively well known how to do that, just create a still. But I don't know how they do it in space. But once again, the engineers have assured me that it's possible.
People you want to talk to are at Coca-Cola. They can do water filtration like nobody else in the galaxy.
Well, exactly. I mean, I honestly do not know. I've asked lots of questions, but I can't claim to understand all the engineering aspects. But certainly removing particulate matter should be simple enough, forcing it through some kind of a ceramic filter or something, and then removing molecular contaminants. There must be some way to do that. I don't know. I honestly don't know. Sorry.
I think we have time for one more question. You, sir.
I'm interested in what degree of competition TransAstra faces. Like, I'm assuming there are other companies that are trying to use straightforward mining. Maybe they're approaching NIAC or like similar venture capitalists. Do you feel like there's enough to go around, or do you feel like there's this race going on? Like, what does that environment kind of look like in terms of competition?
When I first got into this business, I've been reading about asteroid mining since I was younger than you, a teenager, and they always showed these crazy pictures of this big mining industry sort of sticking out of an asteroid, and it just seemed completely unbelievable, and they still do that to this day. But when I first got into this business, there were 2 or 3 other asteroid mining companies that had a lot of flash that were being advertised all around the country and the world. They had some big name venture capitalists who were pumping a lot of money into it. And they had what I would call sort of a more traditional viewpoint or take on how to mine asteroids. And they don't exist anymore. TransAstra came out at the same time with this idea and a sort of a slower growth plan, but I think a more rational growth plan and a better, more viable idea. And so they've survived. And not only have they survived, but they're thriving and growing where the others fell away. And then so right now, there's TransAstra's in competition with other groups for lunar mining of water. But again, they have good ideas, but I'm not involved so much in that part of the group. I don't think there's any sort of active competition at the moment for asteroid mining. There's reasons for that. Then a lot of people sort of say that, well, the reason that ULA, the United Launch Alliance, offered $10,000 a liter for water 10 years ago was because that was before SpaceX can launch all the water into space now. And of course, that's valid. Now the price point for water in space is much less than $10,000 per liter, but it was a nice number. It gave me the nice $1 trillion reference. But the thing is that people seem to forget that our major cost for our price point is the cost of launching our launch vehicle. So if the cost of launch vehicles goes down, then our cost of mining the water goes down a lot too. So we can also drop our price, our price point for water when we bring it back to be economically viable. And so, even though there's 100% uncertainty on virtually every number we're talking about, there's reason to believe that we can still be economically viable even with the competition from SpaceX and other companies.
The one thing business school students will tell you is that once you put all of that risky venture capital up front, do your proof of concept, show that it works, and you get the Jerry Maguire line, show me the money, you'll have all the competition you need. Ladies and gentlemen, Professor Rob Jedicke. So, Professor, thank you for leaving Oahu on a day like this. We have in a lovely packable tote bag a number of tchotchkes. That does not include a winter coat, but those are available through the catalog and the website of the Notre Dame bookstore. Thank you for being with us today, whether you're online or in the room. On Friday next, the 8th of April, Marina Brozovic from the Jet Propulsion Laboratory, chief of the Planetary Observational Group and the Near-Earth Object Team that tracks ill-intentioned asteroids, will be here to talk with us. We'll be in Jordan Auditorium. See you then.